We've ended the last video with this equation right here, and that equation is just an equation which relates the old Hamiltonian h to the new Hamiltonian k through the generating function s right here. What we're gonna do in this video is just like we'll try to get the Hamilton Jacobi equation from this equation right here. To get the Hamilton Jacobi equation, we'll just try to pick up this s right here as to make this k equal 0, and that's it. That's the derivation of the Hamilton Jacobi equation. It's all about picking up the appropriate s as to make the k here, the new Hamilton, equals 0. So this gives us the following equation. Eventually, h as a function of q and p, the vector p and t, right? That's all equals 0. So far so good. That's the Hamilton Jacobi equation. But not yet in the form we want to for our work. And that's what we're gonna do in this video. Okay, so we write this equation here in a more different, readable, in a more way that's gonna give us clue as to how to solve this Hamilton Jacobi equation. So let's just do this. First of all, we have to write down the new Hamilton's equation. Those are partial k, partial p, the vector p capital equaled q capital, the vector q capital dot, right? There's a dot here to indicate that we're taking the time derivative for this vector q right here. And because this one right here is equal to 0 as we've mentioned, this will all give 0 here, or this one right here is going to equal 0. So this tells us that q actually is a vector, and we're going to call this beta, the vector beta. Okay, let's write down the other Hamilton's equation. Partial k, partial q, the vector q as well, the vector q capital, equal the vector p capital, right? And because for the same reason, this k right here is equal 0, this means there's a dot here. This means that this p, the vector p dot is equal to 0 as well. It's equal 0 as well. And this tells us that this p is actually constant as well. So this means we're transforming our old canonical variables to some new canonical variables which are constant of motion. They're not changing with time. They're constant all the time. They're constant all along. Okay, so actually that's cool. So far so good. That means we can write down the Hamilton Jacobi equation in the following form. But actually no, I'm just gonna mention all the equation I need to rewrite down the Hamilton Jacobi equation all in here. Okay, what about the other equations? I'll now introduce two more equations which are relating the generating function s with different variables, with different canonical variables, but I'm not actually gonna tell you exactly why they're right. You're gonna take those for granted. The first one is partial s, partial q. The vector q is equal to the vector p. The old canonical variable are related through this equation. The other equation tells us that partial s, partial p, the capital vector p equal to the capital vector q. So far so good. So those are all the equations we need to write down the Hamilton Jacobi equation in the form we want eventually. So this equation right here, this equation right here, and the other two, and the other. Okay. So let's rewrite down the Hamilton Jacobi equation. As we know, partial t, the function s, and this function here is a function of one of the old canonical variable q and one of the new canonical variable which is p, the p capital. But actually I'm not gonna write down p capital, I'm gonna write down alpha from here, right? So alpha, the vector alpha, and t plus h, and that one is a function of q MP, P small actually, but I'm not gonna write down P small, I'm gonna write down its substitution from here. Instead of the vector P small, I'm gonna write down partial S, partial Q, the vector Q, and T, and that's all equals 0. And that's the form of the Hamilton Jacobi equation we wanna work with. So that's it for this video. Thanks for watching.